Oxidation reduction reaction. Sodium chloride can be formed by the reaction of elemental sodium and chlorine. In this reaction, solid sodium, which contains neutral sodium atoms, react with chlorine gas, which contains diatomic chlorine molecules, to form the ionic solid, sodium chloride. Ionic solid means a solid formed or held together by an ionic bond, which contains a positively charged sodium and negatively charged chlorine ions. So reactions like this one, in which one or more electrons are transferred, are called oxidation reduction or redox reaction. Many important chemical reactions involve oxidation and reduction. Photosynthesis, which store energy from the sun in plants by converting carbon dioxide and water to sugar, is a very important oxidation reduction reaction. In fact, most reactions used for energy productions are redox reactions. In humans, the oxidation of sugar, fats, and proteins provides the energy necessary for life. Combustion of reaction, which provided most of the energy to power our civilization, also involved oxidation and reduction. An example of this is the reaction of methane with oxygen. Even though none of the reactants are or products in this reaction is ionic, the reaction is still assumed to involve a transfer of electrons from carbon to oxygen. So this explains that we must introduce the concept of oxidation state. Oxidation state, or also called oxidation number of the atoms in a covalent bond, as the provide us a way to keep track of electrons in oxidation reduction reaction, particularly redox reactions involving covalent substance. The oxidation states of atoms in covalent compounds are obtained by arbitrarily assigning the electrons which are actually shared to particular atoms. We define the oxidation state or oxidation numbers of the atom in a covalent compound as the imaginary charges the atoms would have if the shared electrons were divided equally between identical atoms bonded to each other, or for different atoms, were all assigned to the atom in each bond that has the greater attraction for electrons. Of course, for ionic compounds containing monoatomic ions, the oxidation states of the ions are equal to the ion charge. So here is the rule for assigning oxidation state. So for the oxidation state of an atom in an element is 0. Example, sodium, oxygen, ozone, or mercury, or any naturally occurring elements. They have a neutral charge, meaning their oxidation state is 0. For the monoatomic ion is the same as its charge. Example is sodium chloride, which has a monoatomic ion of sodium with a positively charged and chloride or chlorine with negatively charged ion. Then we have fluorine is -1 in the compounds, such as hydrofluoride. Its um, oxidation state is always -1. Oxygen is usually -2 in its compound, exception for peroxides containing -1. So for dihydrogen oxide or water or carbon dioxide, the oxidation state of oxygen is always -2. For hydrogen is +1. In its covalent compound, hydrogen, uh, such as for water, hydrochloride, has a oxidation state of +1. So the application of these simple rules allows the assigning of oxidation state in most compounds. To apply these rules, you have to recognize the sum of the oxidation states must be zero for an electrically neutral compound. Again, I repeat that the sum of the oxidation state must be zero or neutral for an electrically neutral compound. So it is worthwhile to note at this point that the convention is to write actual charges on ions as N plus or N minus, the number being written before the plus or minus sign. On the other hand, oxidation state, not actual charges, were written as positive N or negative N, the number being written after the plus or minus sign. Okay, so let's have an example of assigning oxidation state for the following compound. So first we have carbon dioxide. So using the rules already stated in the table, so for the oxygen, we will assign its value of -2. So the oxidation state of the carbon atoms can be determined by, again, recognizing that this compound is neutral or has an oxidation state of 0. So the sum of the oxidation state for oxygen and carbon must be 0. Okay? So since that we have two atoms of oxygen, the carbon atom must be assigned an oxidation state of +4. So that when we added this oxidation state, we have +4 plus 2 atom of -2 for oxygen, we're going to have 0 or a neutral charge. So this is the oxidation state for each element in this compound. Okay, so let's have number 2. Sodium hexafluoride. Okay, since we have a rule for fluorine, so let's assign first for its oxidation state, which is -1. For each atom of fluorine. Okay? And the sulfur must then be assigned an oxidation state of positive 6. Okay, so to balance the oxidation state. So if you're going to add this one, the oxidation state of sulfur to the oxidation state of fluorine, which has an 6 atoms, then we're going to have 0. Okay? So the oxidation state for sodium is positive 6, and for fluorine is negative 1. Okay, so let's have number 3. NO3 negative. Okay, so again, let's put first the oxidation state for oxygen, since already stated in the rule that it always has a negative 2 oxidation state. Of course, aside from or exception for peroxide, which has a negative 1. Okay, so because the sum of oxidation state of 3 oxygen is negative 6, and take note of this, we have a net charge on this compound of 1, negative 1. Therefore, the nitrogen must have an oxidation state of positive 5. Okay? So that if you're going to sum its oxidation state, 5 plus 3 atoms of negative 2 for oxygen, we're going to have a result of negative 1, which is equivalent to the net charge. Okay? So take notice of this, of how I write the symbol for charge. Okay? So this is what is stated in the table, that if we're going to write for the actual charge, the sign positive or negative must be put at the right side of the number. Okay? And for oxidation state, it should be before the number. Okay, therefore, the assigned oxidation state for this compound for nitrogen is positive 5, and for oxygen is negative 2. Okay, so let's move on. Characteristics of a redox reaction. So oxidation reduction reaction or redox reaction are characterized by a transfer of electrons. So oxidation is an increase in oxidation state, meaning it has lost electron. And for reduction, it is a decrease in oxidation state, meaning it gained electrons. So take note of the analogy in the way we characterize or define oxidation and reduction. Okay, so let's have this reaction of sodium chloride. So we're going to find or determine which is the oxidizing agent and the reducing agent in this reaction. Okay po? Okay, so let's assign first the um, oxidation state for each element. So for sodium, we have 0 since it is an element, a free element. And for chlorine, also 0. And for in sodium chloride, we're going to put here for sodium is positive 1 and for chlorine is negative 1 since they are monoatomic ion. Okay, so sodium is oxidized. Why? Because the it there are there is an increase in oxidation state, meaning as we can see here that from the reactant sodium we have zero oxidation, then it increased into positive 1 oxidation state, meaning there is occur an loss of electrons. Therefore this is where the oxidation occur. Okay, and for chlorine, as we observe, the oxidation state of the chlorine is 0, then in the product, we're going to have negative 1. Therefore, it gained electrons because there is a decrease in oxidation state. Therefore, sodium is being oxidized. Therefore, sodium is our reducing agent. Why? Because this is the donor of electron. While chlorine is the or where the being reduced, meaning this is our oxidizing agent. Meaning this is the acceptor of electron. If we're going to observe in table, the periodic table, we know that sodium is in the group 1. Okay? Meaning it has an excess of 1 electron that placed to it in the it has a 1 valence electron which placed in the outermost shell of that atom. Meaning sodium being has a 1 valence electron is ready or willing or donor of electron. And in this case, for chlorine, since chlorine has a negative 1 um, oxidation state, or meaning he needs additional 1 electrons because chlorine is placed in the group 7, meaning it has 7 electrons and need another additional electron to be stable. Okay? Therefore, chlorine is the acceptor of that electron. Okay, so again, let's have another examples. Okay, so now we have the reaction of combustion of methane. So first, let's put the oxidation state. So for hydrogen, we have +1, and for carbon, to make it neutral, we're going to put here -4, since hydrogen has 4 atoms. And for oxygen, since it's a free element, it has a 0 or neutral charge. For carbon dioxide, oxygen has -2, carbon has +4, and for water, hydrogen has +1, and oxygen has -2. Okay, so note that the carbon undergoes a change in oxidation state. Okay, so let's write the reaction for carbon only. So from methane, CH4, carbon became CO2, wherein in the reactant it has a -4 oxidation state, and in product it has a +4 oxidation state. So from -4 it became +4. So that such change can be accounted for a loss of electron. Okay, so since we know that carbon lost electron, let's determine how many electron does it lose. And to do that, we have to add here at the product electron. And the symbol for electron is E with an exponent of negative, meaning it is a negatively charged ion. So what it must be the integer to multiply in this electron? How many electron does carbon lose? Okay, so to do that, we must balance the left side of the reaction and to the right side of the reaction. So we're going to add at the product 8 electrons. So that if we're going to add 4 to 8 of -1, since electrons has -1 charge, it will be resolved to -4, which is equal to the right side of the left side of the reaction. Okay. On the other hand, let's examine oxygen. So for oxygen, we can observe that, okay, let's write here. So we know that the oxidation state of oxygen is 0, and at the product side, it has um, -2. So the total oxidation state of oxygen at the right side or the product side must be equal to Okay, negative 8. Okay, so since we have um, one molecule of dioxide, so we have negative 2 plus 2 molecules of water, so 2 times oxidation state of oxygen, which is negative 2, we have um, negative 4. Sorry, we have here 2 atoms of oxygen, so we're going to have negative 8. So to balance this one, we have to add additional electrons in the reactant side. And this time we're going to add 8 electrons so that we have a balance of negative 8 in the reactant side, which is equal to negative 8 at the product side. Okay, so we can say that carbon here is being oxidized because there has been an increase in oxidation state, from negative 4 to positive 4. So formally, there is a loss in electron in carbon, which is 8 electrons, while oxygen is being reduced because there has been an decrease in oxidation state from 0 to negative 8. So meaning it gained electrons. Okay po. Therefore, CH4 or methane, where is the carbon compound is originally, is our reducing agent, while oxygen is the oxidizing agent. I hope this example is clear with you. Again, I'll just repeat that the oxidation is where the increase of oxidation state occur, meaning it being oxidized or it has lost electron. So since it is where the oxidation occur, meaning this is the oxidation agent. While reduction or the gain of electrons occur will occur at the reducing agent. Okay, so now let's check your understanding. So part 1, assign the oxidation number or oxidation state for the following compound. And part 2, try this one. So for each reaction, identify the atoms that are oxidized and reduced, and specify which is the oxidizing and reducing agent.